Hello, in this video we continue our discussion on logic. At the end of the first part, we saw that when a statement B can be deduced from a statement A, there is absolutely no guarantee that statement A can also be deduced from statement B. Let us consider some less trivial examples. If the temperature of body tissues increases under the effect of some electromagnetic waves, then these electromagnetic waves are harmful. Indeed, this is true. However, its contrary is not. If some electromagnetic waves are harmful, then the temperature of body tissues will increase under their effect, which would be tantamount to saying that if there is no increase in the temperature of body tissues under the effect of some electromagnetic waves, then these waves are not harmful. This is, however, what had been assumed. Indeed, absorption of energy by dead matter is always accompanied by a rise in temperature. And hence, the decision had been taken to go down the road of wireless technologies, since the waves coming from our antennas have neither the intensity nor the frequency to provoke thermal effects, except at the high range of fifth generation waves, in other words, 5G. However, biological tissues are far more complex and organized, and hence are of a different nature from dead matter. And hence they may suffer biological effects for other reasons. And the waves coming from our antennas have very specific properties. And due to these properties, they disrupt the currents in our bodies, the electric currents, which control a lot of our physiological functions. And therefore, these waves disrupt these functions. Here is another example. We often hear, if levels of CO2 in the air rise, then there will be warming. However, there is serious empirical data showing that it is rather the contrary which holds. Namely, if there is warming, then there is a rise in the levels of CO2 in the air. If this is indeed correct, then reducing levels of CO2 will have absolutely no effect on any possible warming, since the rise of levels of CO2 would then be the consequence and not the cause of the warming. In fact, the error made from mistaking the direction of an implication is to go from particular cases to more general ones. For example, from the particular effect of a rise of temperature of body tissues to the more general statement of the harmfulness of artificial electromagnetic waves, which have multiple other effects. This brings us to the question of induction. Induction consists indeed in going from particular cases to more general ones. In other words, it consists in generalizing. Let us consider an example. Until today, day has always preceded night, and therefore it will be the same tomorrow. However, we cannot be sure. It is not an automatic consequence. Furthermore, induction can lead to errors or difficulties, as in the following example. All the swans I have observed are white. Therefore, all swans are white. We know this to be false. This error would make it difficult for us to understand black birds which resemble white swans in all respects except for color. We will be forced to make a special study of these black birds instead of applying our knowledge of white swans to them. Without induction, there can be no science. If we remain attached to observed cases, each time we are confronted with a new case, we are forced to redo a whole line of reasoning. This makes it impossible to predict. But we must be careful when we generalize. Induction goes beyond analysis. It involves creativity and is a matter of opinion. Unlike deduction, it does not follow strict rules. The big problem with induction is, of course, how to justify our knowledge of unobserved cases based on observed ones. To understand induction better, let us, like Karl Popper, associate to each observation a point on a graph. Then a scientific statement would be a curve passing through a finite number of points. However, there are many curves passing through any given finite number of points. Taking this analogy a step further, the degree of generality of a statement would be the length of the curve. If there is more or less one specific curve passing through the points between two extreme points, then we would choose that particular curve. But the wider you want the curve to be, the greater will necessarily be the extrapolation made. In other words, the more general a statement is, the more it must be based on assumptions, and the more exceptions there could be. A curve illustrating a so-called universal law of nature would be unlimited. If we brush aside this question by saying that the aim is not to deduce the color of swans from the observation of yet more swans, but to arrive at basic principles from the observation of a variety of dissimilar cases, then we do so at our peril. Because too little data can lead to erroneous models and therefore to erroneous predictions, as was the case in 2004 when we were unable to predict the tsunami that occurred in Asia and its range. It is estimated that more than 200,000 died. Since then, we have accumulated far more data, but to what extent can we say that what applies to one region at a particular moment can be extrapolated to another region at another moment? To predict is to say that when an event A occurs, event B follows. But this is not establishing that A is the cause of B. Causality is extremely difficult to determine. To date, night has always preceded day, but night is not the cause of day. Or the presence of a pathogen in our body does not necessarily imply that illness will follow. Indeed, 1/4 of the world population is estimated to carry the tuberculosis bacillus. However, according to the World Health Organization, only 5 to 10% will actually develop tuberculosis. Hence, this means that if indeed this suspected pathogen is the cause of tuberculosis, then other conditions must also be present for the illness to develop, and we must identify these conditions. Or else it might be even necessary to envisage the possibility that there is no pathogen causing tuberculosis. So antecedence is not enough. Showing A implies B is not sufficient. Now, each time I throw a red javelin, it follows the same trajectory as long as I throw it in the same manner. However, the color red is not the cause of the movement, because if all other conditions remain the same except for color, then throwing another javelin of a different color in the same way will make it have the same movement. We must show unconditionality. In other words, we must show that if A is absent, but all other conditions remain the same, then B does not take place. That is, non-A implies non-B. For example, if we suspect that an agent is the cause or the cause of certain clinically diagnosed symptoms, then in the absence of this agent, all other conditions remaining the same, these symptoms should not occur. That is, there should not be any cellular degradation or death. To be sure of this, control experiments need to be carried out. However, it would seem that as early as 1954, at least in the case of measles, it was found that when non-infected tissue was used, all other conditionings being maintained, in particular the usual experimental method, this effect was still produced, namely there still was degradation or cell death. It could therefore be that it is the experimental method and not the suspected agent that is the cause of the degradation or cell death. To prove causality, it is therefore essential to ensure that both A implies B and B implies A under similar conditions. In other words, for A to be a cause of B, A must be sufficient and necessary for event B to occur. But even this is not enough. A and B could be co-effects of another cause. For example, there is heat and there is smoke at the same time. However, heat is not the cause of smoke. The cause of both is a wood fire. Another example. If we display certain symptoms, it means that there is degradation or death of certain body tissues, and many bacteria are found on the site. However, it cannot be concluded that the bacteria are necessarily the cause of the death or degradation of tissues, that is, of the illness. Indeed, they could be playing a role of scavenger by nourishing themselves on the dead tissues and therefore enabling their regeneration. The fact that trillions of bacteria are present in our bodies and that they play a vital role to keep us in good health would tend to support this conclusion. In other words, the presence of the bacteria and the illness would be the co-effect of a different cause. However, Koch postulates, namely the basic reasoning used to ensure that a disease is bacterial, do not allow us to conclude whether or not the presence of bacteria is a co-effect or a cause of the disease. Let us consider an example that illustrates another issue. We know that if there is a wood fire, then there is smoke. But someone might say that the wood fire is not the cause, but that the cause is an invisible demon that intervenes just before there is smoke. From a purely logical point of view, that makes perfect sense. And who knows, there might be some demon indeed, but the scientific approach of our study of the sensible world implies verifiable conclusions. In other words, conclusions based on empirical data. This is far from being an insignificant remark. We have to be very careful when it comes to the microscopic world, which we can never observe in its natural state, but through instruments, and therefore only after preparation of the samples and these preparations change their properties. When can we then conclude with a modicum of reality that what we observe has the desired properties? Is this really the case with germs? Serious doubts seem to persist. In conclusion, neither logic nor observation can lead to firm conclusions. The art of science is precisely to try to understand the sensitive world as best as we can by circumventing these obstacles to the best of our ability. In the end, this understanding can only be negative. It can tell us what is not, but it can only affirm with great difficulty what is. Nevertheless, to quote Leo Tolstoy, science is as necessary to man as food and drink and clothing, even more necessary, not because we decide that what we call science is essential, but only because science really is essential. Science is powerful when we recognize its limits, which are the limits of the human condition, the limits of the human mind, of human perception. The danger comes when we claim to know in the name of science what science is incapable of saying and admits its incapacity to do so. Thank you.